Thank you, everybody, for being here also in this afternoon. This afternoon, we will assist to a very interesting session that is dedicated to the relationship between quantum computing and HPC in Europe. For this purpose, we invited a lot of European supercomputing centers in order to explain their vision about quantum computing and, of course, high programming computing. So the first speaker is Dr. Ariana Torres-Knoop, that is advisor and project manager of quantum computing area at SURF. Thank you, Ariana. Thank you very much for being here. I leave you the floor.
Yeah, thank you. I will start by sharing my screen.
Yes.
I hope you can all see it.
Yes, we can see it.
Perfect.
Thanks a lot.
Thank you for the invitation. I'm quite happy to be here in this
pleasure.
Edition of 2021. Yeah, as Daniel was saying, my name is Ariana and I work at SURF. So I guess the first step is to really tell you what SURF is, because I am not assuming you guys know it. So SURF is basically the Chineca of the Netherlands. It's a bit smaller, but it's the collaborative organization for ICT in the Netherlands. And we do different things. So we do data storage and management, network infrastructure. We also are involved in a lot of educational tools, but maybe more relevant here, we are the managers of the HPC system, so the high performance computing system. Here's like a picture of the high performance computing system. We actually got a new one recently now in September, so we're quite happy, but it's having a lot of issues, as it happens when you get a new one. We're located, as mentioned, in the Netherlands. The supercomputing center is in Amsterdam. But we actually have also an office in Utrecht, which is about 20 km from Amsterdam, and that's our main office. And if you want to know more about it, feel free to go here. So let me start by, I'm going to try to describe a little bit the process we went through from, being completely quantum ignorant to try to get somewhere closer to quantum knowledgeable. I'm not claiming we're there, but still getting closer. And the story started because a couple of people some years ago began asking, hey, when is a quantum computer going to be in your high performance computing center? Are we going to get access? And we were, to be honest, we didn't even know what to answer. So the first step was to really figure out what this quantum computing was about and try to be able to reply to these questions. So we figured it out. We realized we were probably several years away from that. So, we're a bit relaxed. But on the other hand, we also realized that if people are asking for this, is because it's maybe an interesting stuff to put our attention. Most importantly, because as IT centers or businesses, we need to understand and grow and update with the users or with the customers, because it evolves so fast that we don't want to become obsolete. So we really need to hear what they want and where they are evolving towards in order to move with them. So we started just wondering, is this quantum computing really like the thing we need to move towards? So let me just share with you, this is an old plot, but it's still like quite representative of, let's say, the fields that use our HPC center. And what I can tell you is that this a big chunk or a big portion of the pool is users that use the HPC cluster for chemistry and material science simulations. And another big pool of users, so let's say, some earth science, climate, astronomy, bioscience, those are fields that are more and more using machine learning tools to solve their problems. So we really, if we want to stay relevant for our users and support our users, we really need to understand where these two fields are moving. And so suddenly quantum computing wasn't such a strange thing to learn and to try to invest in, because these two are in principle, let's say, the killer applications of quantum computers. In particularly, chemistry is really expected to be the application. Why is this? Because quantum systems are very difficult for a classical computer to simulate. The fact that the quantum systems have this uncertainty makes it very complex to simulate in a classical computer, as opposed to a quantum computer where the intrinsic quantum nature of the qubit makes it a very easy map. Well, easy, let's not claim that. So chemistry is really expected to be the killer application. And just as a little intermezzo, some of the problems that people are really expecting to solve with quantum computers are things like photovoltaics, solar cell materials, nitrogen fixation, high temperature superconductor. And even though quantum computers do not solve any other problem, if they manage to solve these problems, that's already a game changer worldwide, because they have a really big impact in today's world. So anyway, we decided, okay, we have a lot of users that might move into the quantum computing technology eventually. So let's try to understand a bit more. So our question was, what is the role of an HPC in the quantum era? Because it wasn't really clear to us, right? So we just dig in this a little bit by asking, by researching. And we came with the following. I apologize for this thing at the top. I don't know how to remove it. But we basically came with the following. Let's try to understand our role, let's say, today, when we have only small quantum computers, our role, let's say, when we have 1,000 qubits, and our role when we have 1,000,000 qubits. And you can see that I was very smart not to put times, because, well, we don't really know when this is happening. There are, of course, already some roadmaps from IBM and Google, but let's not put time. Not putting time is a bit safer. But anyway, today, what is our role here? Or what is the role, let's say, of quantum computing versus classical computer? So quantum computing nowadays is not used really to show quantum advantage, because there's still too little the systems. But what we are doing when we use quantum computers is we are trying to understand and characterize the hardware. So really see how the algorithms work, how reliable it is, how do they perform, how do they scale, etc. Classical computers, on the other hand, in this scenario, they're used mostly for emulation. And this is important because this can help for a simulation-driven co-design. So we can really sort of use these emulators to debug our algorithms and to develop and test further. The other thing what classical computers are still used for is what is called quantum compilation. I'm not going to go into the details of that, but it's basically preparing the circuit for the quantum computer to take it. So then this is more or less here, right? So we need a classical computer for emulation, and in particular, we need an HPC the moment we pass a certain amount of qubits, because we have a memory issue. So beyond, let's say, 25 qubits, that doesn't fit in your laptop. So you really need something with much more memory. So then we ask, okay, in the future, let's say we have 1,000 qubits. Well, then we are assuming that quantum computers maybe are able to already show quantum advantage by performing, for example, hybrid algorithms. So we might be able to already offload some classical tasks. So that's what quantum computers will be for, together with everything that they were used before. And classical computers will most likely still be important, for example, for pre and post processing of data. So really to prepare the state, to analyze the outputs, to do the quantum error correction, and so forth. And then the question was, okay, and what happens then when we really have like fault-tolerant computers, hopefully? And so then, you know, what is quantum computing going to be for? Again, we're going to be offloading tasks for fault-tolerant algorithms, and the classical computers are still going to be used for all the above, but maybe also they will help to accelerate in some way the quantum circuit. So maybe in this case, the classical computers will become the coprocessor. So basically there are like three main scenarios that we see how quantum computing is going to be, like how HPC and quantum computing are going to interact. The first one is that it's going to be for quantum accelerated classical computers. So when we offload some tasks that are classically difficult into a quantum processor. The second way that we see it is that there are going to be classical accelerated quantum computing. So this is the use of classical resources to accelerate the execution of quantum circuits. This is, for example, the approach that a startup called Epic has taken, where they take the circuit and they propose it should be subdivided in circuits, and then those parts of the circuit can be executed either in a quantum computer or in an HPC simulator emulator, because maybe that could give some advantage. For example, if you have very sparse circuits or Clifford-based circuits, this could be a way to go. And then the third scenario we see is that classical computers will be used for supported quantum simulation. So really use classical computing for pre and post processing of data beyond state preparation, beyond quantum error correction, which we can consider part of an algorithm. And in all these scenarios, what you can see is we're always talking about this sort of feedback between classical and quantum computers, right? It's always this hybrid computing that comes into play. So then the next question is really, okay, these are two hybrid things. We have really two completely different technologies. How are they going to interact? So this is something that we came up. It's by no means official, but we thought, okay, let's try to understand how they will interact. So we thought these hybrid workflows are going to be either local HPC, local QPU, HPC, HPCQPU. Now, what does this mean? This is basically where you're going to execute the classical part, where you're going to execute the quantum part. And here, local, we refer to anything that fits, let's say, in your laptop. So I'm just going to claim smaller than 20 qubits. Depends a lot on your laptop. An important thing is that every quantum or every hybrid workflow, every quantum execution will always have a bit of a classical, a bit of a quantum part, and it will always fall in one of these scenarios. And what is important about these scenarios is that depending on how they are coupled, it says a lot of how you need to orchestrate or how you need to manage this communication, right? Like it's not the same if you have local, where everything is happening in your computer. So you have the classical part in your computer, the simulation in your computer, and then you basically know all the resources very easily. It's easy to orchestrate. It's not the same to do that to use something, for example, like a local HPC or local QPU, where you really need to figure out how to share the information about the resources available in the different places. In particular, keep in mind that for the quantum computers, it's not yet clear how we will couple this, right? I mean, of course, it would be nice to have our quantum computer in the HPC centers, but this is there has a lot of issues as well. So most likely this will maybe be like a cloud-based service. So you can imagine that the way that the classical and the quantum part are coupled really will change a lot how we have to execute these workflows. And just to mention it, I'm not saying any of this is exclusive of each other. In fact, we should have codes that are portable through this whole sort of workflow, because the way they are displayed, it's also a bit like the developing cycle, right? So you start with a small experiment in your computer, then maybe you want to increase the number of qubits, so you use an HPC, then maybe you want to test how does it work with an actual quantum computer, so then you move to the next one, then maybe you want to test several different parameters, and then you move to an HPC, and so forth, right? So we want codes and we want orchestrations that are sort of portable through the different scenarios. So with all this knowledge in mind, this is what we had learned about quantum computing, among other things. We thought, okay, what do we need to do then? How do we help our community to jump into quantum computer? And then we came up with a couple of ideas. We decided that we needed to support the access to emulators and simulators, as well as classical quantum computers, We would need to support the integration, so really this orchestration and how do you integrate the quantum and classical ecosystems. Stimulate the development of quantum applications, because this is still missing a lot, and this can help us a lot figure out how to integrate things. We wanted to support, obviously, also the development of tools and everything that is needed to transform classical applications into quantum applications. And in general, we just want to help our community and our users to take advantage of quantum computing. So some activities that we took in order to do so, we bought some high memory nodes. This is important for quantum simulation, because you very fast reach problems in memory. We also gave access to emulators, access to some QPUs. We had the QLM Atos for a while. I'll go back to that in a second. We started close collaborations with a couple of QPU developers to really study, like, how do you access, how do you schedule, how do you do standardization with different platforms. Then we also started doing, for example, working with universities, because we do not claim to be the most knowledgeable place in quantum computing. This is in the research centers and universities, but it's important to interact with them to really gain knowledge from them and share our knowledge from HPC with them. So yeah, we participated in a lot of different activities. As shown here, some worked, some did not, and let me just say a bit why. So the QLM Atos, we had it for a while. We still have it actually at SURF, but we never really had enough users. So we had maybe of the order of 3-4 users, and that for us was very difficult, because obviously it requires maintenance, and it wasn't easy to justify doing all this just for 3 or 4 users. So at some point we decided we needed to let this go. This was before my QLM, which for those of you who do not know, my QLM allows to use different languages. Before that, you really had to use the Atos sort of like programming language. So that made it very difficult. But what we did instead is we bought these high memory nodes, right, a bit to sort of compensate for the loss of the QLA machine. The second part that also didn't work out very well is to offer sort of standard HPC access. Most of us are used to maybe connect via the terminal SSH, but actually the quantum computing community, they are not that familiar with HPC centers, and they also don't want to go through the trouble of understanding. So what worked out very good for us was to create a Jupyter hub where they could really just work the way they were used to, but then the Jupyter hub was connected to the nodes, these high memory nodes. So they really liked that, and that was actually very successful. Some other things that didn't work for us, we created a Singularity container with a lot of emulators and other packages that we thought were useful. The problem with that is that in quantum computing, again, there's still too much development going on. And the problem with the Singularity container is that you have it sort of isolated, so you cannot really play with it too much. So people were not that happy with it, but what they did appreciate was the usage of easy build installations. I don't know, I'm not going to go into the details of that, but it's basically optimized installations of specific software or specific simulators. And then we had a couple of other good things that work out from the beginning, like internships, collaborations with quantum providers, financial support for use cases. I will showcase that in a second. And we're currently basically working on how to give access to actual QPUs, and we hope that this is successful. So let me just mention a bit about this financial support for use cases. So what we did, we wanted to learn quantum, and we wanted to have use cases. And well, the researchers, they always want to have funding. So we thought, okay, let's try to figure out if we can do a win-win situation. So what we did is we worked together with Leiden University, the FU, and the University of Amsterdam, and we came up with a proposal to work in quantum chemistry algorithms. So the deal was basically we would give HPC resources and support. We would give my time to some extent, and we would also finance a postdoc for a year. And so we did this. The idea was really to support the development of algorithms in quantum chemistry. And it was pretty successful. So what we did is four things. We were working in interfaces to classical software using OpenFermion. We were working in improving the classical optimization, the ansatz optimization. And the fourth step of the proposal, of course, was how do we disseminate this knowledge to really justify doing this investment. I don't have all the results yet, but there was definitely one paper that came out of that, which is reinforcement learning for optimization of variational quantum circuit architectures. And overall, it was a really great experience. We learned a lot, they learned a lot, and we're still collaborating further on these projects. And in the same line, we actually, because it was so successful, we started two more projects in these lines. So one is ray tracing for atmospheric simulation. So again, we're working with quantum algorithm experts, with the providers of the problem, and with us, and all together we're trying to figure out how to tackle this. The second one we have is about pattern recognition and ray tracing in high energy physics. This is together with two universities here in the Netherlands and CERN. And beyond that, we have also our own sort of internal projects, which are tackled by our employees, but also by interns and master students and so on. And yeah, we're just trying to learn as much as possible, get as much knowledge as possible. And in general, we try to also create Jupyter notebooks that are accessible for the public. I would add here the link, but I'm still working on it. So if you jump in the SURF link, maybe in a couple of months, you will get a lot of notebooks for different projects that we have worked on. So just to finalize and keep this on time, I think as HPCs, we need to get ready for quantum. We need to understand our users. We need to understand that some users might benefit from this, and therefore we should be able to at least give some level of support. There are some simple initiatives that we can start to learn as HPCs, but also to stimulate and support our users. And I think it's important to also acknowledge that it doesn't matter even if it's now or when actual quantum computers are fault tolerant. Quantum computers will always be hybrid to some extent because you always need the support to some extent of the classical computers. So I think it's very important to focus in how to enable this communication between the different devices to really get the best possible performance. And with that, I would like to finish, and I hope I'm on time. And I'm open for questions, obviously.
Yes, you're more than on time, Ariana. Thank you. Thanks
Well,
a
it's
lot.
always good, right? I mean, normally these
Yes,
things
no. Always good. And let's wait for some question. And I want to remember that everybody can also ask questions, simply raising their hands. Oh, we have a question. So it says, can you give us more details on the RLL approach, the restricted learning approach?
Yes and no. I mean, I'm not the big expert on this. Yeah, I'll try to answer to. I saw the two questions in the chat.
Okay.
So I would like to refer you to the paper. I can paste the link in a second in the chat. But the main idea is really how to create the ansatz instead of trying to use the hardware-based ansatz or a hard-to-fuck-based ansatz, like really create it by exploring the space of ansatz using reinforcement learning with certain. So the main idea is to really how do we create smaller circuits, because the problem with ansatz is normally is that they create really long circuits. So this is something you want to minimize. But I can put I'm not a machine learning expert, to be honest, so I'm not gonna attempt to explain the methodology. But yeah, it's quite nice, good results. I'll share the paper in a second.
Thank you. I'm interested too.
Yeah, so the second one, is there an open source repository for projects in ray tracing? This is a project we're starting actually now in 2022. As soon as we have a repository, I'm happy to share it. I mean, we work open source in general. We have a couple of ideas, obviously, on how to do ray tracing, and there are a couple of papers also there, about ray tracing, treating the problem either as a sampling problem or as a just linear algebra problem, depends how you want to see it. But we haven't started the coding, let's say. But yeah, if you keep an eye for the SURF website, we probably will put a link as soon as possible. But we are pretty excited about that project. We think it's, we have already worked in ray tracing with the Wageningen University using machine learning. So the idea now is really like, how can we now extrapolate this into something else? See if we can do something.
Very good. Let's see if there's something also here in YouTube. No, YouTube, we have no question here, but okay, I want to ask you a question. Okay, we have...
was Python used for those chemistry applications on Atos machine?
For hybrid application?
What do you mean? So the chemistry project was mostly written using Open Fermion and Circ, I think. So that's related with the QC4QC. So this project we had with Leiden, they didn't use the QLM as far as I'm aware. So that's part of our problem. That I mean, maybe other HPCs have had a different experience, but we just never got enough users. Having said that, nowadays with the Atos machine using my QLM, maybe some other people can comment on that, you can really program in different languages, right? So you really can do Qiskit or Circ or different backends. So that has helped a lot to get more people interested. Because the problem is that before it really needed to be the QLM language. And so, you know, convincing the researchers to use that was a bit problematic. And I see Luigi has a question. So.
Yes, so since I can connect, I didn't want to jump without raising my hand. Well, very nice talk, first of all. I've seen many similarities with the same questions that we have also at the lab, which I'm going to discuss in the next talk as well. It's not really a question, maybe just of comments, a couple of comments on the things that you discussed. For the QLM, we could see as well a sort of a slow start with the users. Now I have to say we get to a regime where we have, I would say, a total of 20 users and maybe half of them running on the machine or a bit less, but with some constant rates. So now it seems like we got a critical mass, but I can see, as you do, some peculiarity in the way the typical users approach the HPC environment. So researchers in quantum computing are more used to work with Jupyter notebooks than with typical SSH, and this poses a challenge also because this is not typical to be done on an HPC center. And I see more or less you showed the same thing. We were also thinking in terms of containers, for example, for making the deployment easier for such users that have less exposure to an HPC ecosystem. And yeah, so I could see many similarities, as I said, with things that we worked on.
Yeah, I think in general it's a bit of trying and seeing what works, right? I mean, as you mentioned, it's difficult. The quantum computing community has not been yet an HPC community, right? So it's just recently that they're starting to jump into the HPC, and they don't want to add, or let's put it differently, we want to make it as barrierless as possible, their integration to HPC, right? So yeah, sometimes that means using Jupyter notebooks in an HPC, which if you are from an HPC background, you will frown upon, right? Seems like the wrong usage of it. So there are a lot of different issues that we have encountered where we thought this is a great idea and then it didn't work. Another thing we tried at some point, so a lot of the codes that the quantum computing users were bringing were Python written and very inefficient. I mean, already the emulators tend to be quite inefficient in some ways. And then the codes were very inefficient. So we thought, okay, let's then create some sort of a profiling tool so at least they can use that. So, you know, you just constantly try to think, what can we give them? What tools do they need? But it's very difficult to try to guess and see what works and what doesn't work. And I think as HPCs, it would be really nice to try to exchange this information, right? Like what worked for you? What was your strategy? How did you communicate it with the people? Because for me, another thing that has been difficult, interested in your experience, is convincing the quantum computing community that they need HPC. I mean, it's not that I want to force it, but it's a bit, you always get the answer, I can run everything in my computer. And then you're like, yeah, up to a certain point, and eventually this will be an issue, so why not start, let's say, the onboarding now? But this is something that I'm always interested to hear, like how have different people tackled, because I don't think it's that straightforward. So yeah, I'm glad that we all experience, I mean, I'm glad to hear that you also have these problems.
Yeah, well, you mentioned another one that I'm aware of, the fact that there might be software that we can make available for the community. We can make available, I would say, on our login interface to the HPC system, but this software itself, most of the time, is not really HPC ready. Yeah. So we have this friction of, yeah, we want to make something available, but what we give is not something that can be run efficiently on our systems.
Yeah, I don't know you, but I get a little bit of a heart issue whenever I see one node of 40 cores with one core in usage and then full RAM completely. I mean, as an HPC background,
it's painful.
It's painful. It's very painful.
Yes, I agree.
Yeah.
No, you're totally right. Thank you, Ariana. Thank you, Luigi, for your intervention. It was very interesting. So
yes.
Thanks for the invitation, and I
thank you for
pass
being
the floor just to be on time.
Yes, perfect timing. So let me introduce
now, unfortunately, I hear my daughter out of the door without keys. So if you allow me 30 seconds, and I will be back for giving my talk.
Not a problem. Not a problem at all. Thank you, Luigi. Okay, maybe in this time, yes, no. You know, it's a real problem to convince quantum computing users that the HPC is really useful in this area. But maybe when we will have the first quantum advantages using hybrid algorithms with HPC, they will see it. But I'm looking right now. I'm seeing that time is passing as going, but people is understanding this particular thing.
Yeah, and I also think that the moment they start using it, they really are like, oh, this is great. Why haven't we used it before, right? So that's also pretty funny. But yeah, I'll give you the floor. Sorry.
No, not a problem, Ariana. Not a problem at all. Thank you a lot. See you.